And notice that we have the big green blob on the F and the blue blob on the hydrogen. What that represents is that fluorine has a higher electron density than hydrogen. Okay, so there's a couple of things to point out to you here is, first of all, if you look carefully, we can see that we have these delta plus and delta minus. What that means is that we have a partial positive charge on the hydrogen and a partial negative charge on the fluorine. All right, so if we were to take a closer look at this chemical bond, we could say that, I'm going to just write it up here, we have hydrogen bonded to fluorine, okay? Because fluorine is much more electronegative than hydrogen, what that tells us that our electron density is much closer to the fluorine than the hydrogen. So instead of sharing those electrons in that single bond equally, they're going to be closer. The electrons, imagine that they're closer over here to the fluorine. So the way that we represent that is we're going to use, we're going to draw our chemical bond like normal. So here's our single bond. But then we can actually use a little arrow with a plus sign. Okay, so what that means is that the hydrogen-fluorine bond is polar, and fluorine has a higher electronegativity. And because it has a higher electronegativity, it has a partial negative charge. That little squiggly d is a lowercase delta. It's still a covalent bond, so the electrons are still being shared. It's not an ionic bond where they get completely transferred over. But the electrons are closer to the fluorine than the hydrogen, so the fluorine becomes slightly positive. The fluorine is slightly negative. The hydrogen is slightly positive. All right, so a polar bond is an uneven distribution of electrons in a covalent bond. Okay, and so when we have a polar bond, we get a partial positive charge and a partial negative charge. And we symbolize that with a little delta plus. The partial positive is going to be on the less electronegative element. This is where the periodic trend of electronegativity comes in. And we get a partial negative and we symbolize that with a delta minus on the more electronegative element. So what we're going to do is, if you look on the next page of your notes, actually it's on page 10, you'll see that there is an electronegativity chart. If you want to compare the electronegatives directly, you can do that here. But for our purposes, we're going to think about this just in terms of fluorine is our most electronegative element. Okay, so this chart is on page 10 of your binder. Fluorine is our most electronegative element, and then we're going to compare electronegativities. So as you get further away from fluorine, you get less electronegative, okay? And if they have the same electronegativity, then it's a nonpolar bond, okay? All right, so the next thing I want you to do is we're going to go to this website, fet.colorado.edu, and I want you to work through this activity. I'm going to show you how this works, and then I want you to work through this using the simulation. molecular polarity and intermolecular forces. This is found on page 11 of your binder. So we're going to work through this lesson together. So what's the difference? Inter versus intramolecular forces. Intermolecular forces are basically just a chemical bond. And nobody really uses that term, but it's just for comparison's sake. We just call it a chemical bond. However, intermolecular forces, i.e. IMFs, you're going to see it as IMFs, is the force that holds molecules together. This is an important concept in chemistry. Okay, so intermolecular forces are not very strong. They're actually much weaker than a chemical bond. So like a covalent bond is much stronger than an intermolecular force. However, those intermolecular forces do exist and they have a big impact on the chemical and physical properties of a substance. Okay, so molecular polarity, the force of attraction between covalent bonds, well, intramolecular forces are very strong, okay? So covalent bonds can be either polar or nonpolar. So the point of this lesson is to kind of give you some ideas about what is a polar bond, what is a nonpolar bond, and then we're going to think about the whole molecule. Okay, so we just talked about polar bonds. There are the unequal sharing of electrons in an atom. Okay, and so when we refer to this, we refer to the unequal sharing as a polar bond, and then a polar bond in a molecule can cause the whole molecule to be polar. Or we could say it has molecular polarity. Okay, so why do we care? So if a molecule is polar or nonpolar, it's going to affect the intermolecular forces, and the intermolecular forces affect the properties such as boiling point, melting point, solubility, evaporation rate, etc., things like that. So the physical properties change. Okay, so let's talk about polar molecules. Polar molecules are said to have a dipole. Okay, so when you say dipole, that's just another way, there's lots of new terminology, to say polar bond. Okay, so a polar bond happens between elements that have different electronegativities. This is very similar to the hydrogen and fluorine example we talked about earlier in this video. So the electrons are more attracted to the chlorine because it's got a higher electronegativity. So this is going to be a polar bond because the chlorine has a partial negative charge and the hydrogen has a partial positive charge. Okay. So the partial negative is on the element in the bond that has the higher electronegativity, and the partial positive on the polar bond is on the side that has the lower electronegativity. Okay, now we have this phrase called a dipole moment. So a dipole moment is the overall polarity in a whole molecule when you add all the polar bonds together. Now, in this case, hydrogen chloride, HCl, has one bond. It's between two atoms. So the polar bond and the dipole moment of the molecule are going to be the same. Okay, but if you have a molecule that has more than two atoms, then you have to take into account the polarity of those individual bonds and how they combine together to give you an overall dipole moment. Okay, so nonpolar molecules such as Cl2 have completely equal sharing of electrons. And it's equal because it's the same atom. They have the same electronegativity. So there's no difference in the amount of electrons distribution in this atom because they're both pulling with the same amount of force. So it's nonpolar. Okay, so here's where it gets interesting. When we have molecules that have more than two atoms, well, all of a sudden we have to take into account not just the polarity of the individual bonds, but also the shape of the whole molecule. So water is a polar molecule. We know that. We learned that in biology and stuff. Now we're going to learn more about why. So each hydrogen-oxygen bond is polar. And the polarity of each individual bond points towards the oxygen, okay? But because water is bent, those two polar bonds do not cancel out. So there's a net positive on the hydrogen side of the molecule and a net negative on the oxygen side. So it's a polar molecule, and we would say it has a dipole moment. So therefore, we have a partial negative and a partial positive for water. Okay, nonpolar molecules are completely symmetrical. Now, carbon dioxide is made up of two polar bonds. The chemical bond between carbon and oxygen is polar. However, carbon dioxide is a linear molecule. So if you draw the structure and you figure out from the Lewis dot structure and the molecular geometry, those two polar bonds completely cancel each other out. So therefore, it is overall a nonpolar molecule. It does not have a dipole moment. So you have to take into account both the individual bonds and the shape of the molecule. All right? So there are two things that you got to work on here. The polarity of the individual bonds and the overall shape of the molecule. So when you're figuring out the molecular polarity, first thing you got to do is draw the Lewis structure of the molecule. Then what you have to do is determine the polarity of the individual bonds. Okay? And then you pull all of those, both of those things together to determine whether the overall molecule is polar or nonpolar. Okay, so let's try one. We have methane gas, CH4. All right, so the first thing we're going to do is draw the Lewis dot structure of the molecule. All right, bang, there it is. We've drawn this molecule in class. Okay, now it's a tetrahedral molecule. So if you draw the molecule, you figure out the shape. Each carbon-hydrogen bond is it's slightly polar, okay? The difference in electronegativity is 0.4, so it is a slightly polar bond, okay? So if we draw all of those in, carbon has the higher electronegativity, so therefore all four of those bonds are pointing inward toward the carbon. Because it's a tetrahedral and it's completely symmetrical, it's going to be a nonpolar molecule. So a molecule that can have polar bonds can still be nonpolar. We saw that with carbon dioxide. It is also true with methane. Okay, what about this molecule, SO2? We've drawn this molecule many times. It's one of my favorites to draw. SO2 has a single bond and a double bond and one lone pair. Okay, well, if you figure this out, that it is a bent molecule, okay? It's not linear. And we also know that these are polar bonds because oxygen is highly electronegative. The difference in the polarity is 1.0. So we have two polar bonds in this molecule. All right, so then we know that our polar bonds are pointing outward towards the oxygen. So we have a partial negative charge on the oxygen and a partial positive on the sulfur. And because the molecule is bent, those two polar bonds do not cancel out. So we end up with a dipole moment or an overall polar molecule. Okay, so our two polar bonds do not cancel each other out. They actually add together to give you an overall polarity to the whole molecule. Okay, here's a little helpful tip. Sometimes people like to think of it in terms of a plane of symmetry. Okay, if you have, go back. I like to use the first steps, but sometimes people like to use the lines of symmetry. Okay, if there are two more lines of symmetry, it's a nonpolar molecule. If there's only one line of symmetry or no symmetry, then it's going to be a polar molecule. Sorry, if there are two or more lines, it's going to be nonpolar. Okay, so if you want to think about it in terms of symmetry, you can use this as a guide. Okay, there's a couple more practice here. So you can go ahead and try those. And I will put the answers up. You can pause the video for a second, try them, and then look at your answers. Okay. notice with this molecule that we have polar bonds, but one of them is pointing in the opposite direction. Okay, so essentially our 4 polar bonds don't cancel each other out. Okay, so it is an asymmetrical molecule. 3 polar bonds are pointing out towards the chlorine, and 1 polar bond is pointing in towards the carbon. So therefore, this is a polar molecule, even though it's a tetrahedral. Okay, so a couple of little things to think about. Whenever polar bonds are symmetrically arranged, they produce nonpolar molecules if it's all the same bonds, okay? Like the example we just saw, if you have a symmetrical molecule, but there's an oddball bond in there, it's probably going to be polar. Okay, molecules with more than one bond, the polar molecules are formed when the polar bonds are asymmetrically arranged, okay? So water is bent. You can also, another thing I like to look for is when you have molecules that have lone pairs on the central atom, those tend to be polar. So if there's no lone pairs on the center atom, most likely those are going to be nonpolar, as long as they're all the same bonds. Okay. So water has a dipole moment, we already know that. And it's asymmetrical, it's bent. It has 2 lone pairs on the center atom, so therefore, all of those reasons make it a polar molecule. Okay, we're going to keep going here. NH3. Try the rest of them in this little box, and we can go over the answers in class Monday. Intermolecular forces are going to be the last part of this lesson, and the forces of attraction between the molecules, and we call them IMFs, or intermolecular forces. Okay, and there are 3 types. Intermolecular forces are generally called van der Waals forces. Okay, so that's kind of the fancy name for IMFs. And there are 3 kinds. It's London dispersion forces, dipole-dipole force, and hydrogen bonding. Okay, and so we're going to talk about each one of those 3 and go through the notes starting on page 13. Okay, so important to note here is that the stronger the intermolecular forces, the higher the boiling point. So the boiling point is determined by, well, some other factors, the pressure as well. But in general, if you have pressure constant, a substance will boil at a higher temperature if it has stronger intermolecular forces, because it's holding, those intermolecular forces are holding those compounds together. Okay? Remember that intermolecular forces are the weak forces that hold molecules together. Okay? Now, within the category of intermolecular forces, the weakest of the 3 are the London dispersion forces. Dipole-dipole forces are stronger, and then hydrogen bonding is the strongest of the 3 intermolecular forces. But don't forget that intermolecular forces are always weaker than covalent bonds. Okay, London dispersion forces. So London dispersion forces are very weak intermolecular forces that happen between nonpolar molecules. So nonpolar molecules really have nothing else going for them to hold them together, okay? And so what it is, it's an instantaneous dipole. In other words, at one given instant, the electrons kind of clump up on one side of the atom, or the molecule, and cause a spontaneous dipole for that second. Okay, so here we have the molecules next to each other. Okay, at one instance, we have the 2 electrons are on one side of the molecule, because remember, electrons can move around anywhere. So randomly distributed, at some point in time, they're going to be this instantaneous dipole, which causes a dipole, oopsies, it causes a dipole on the next one, okay? So if that moment happens, then the neighboring molecule also gets that dipole for that fleeting moment. So it's sort of like this little mini chain reaction. Okay, so it's a very weak force. Oh, isn't that cute? And so the two molecules, when they have this instantaneous dipole, are held together for that moment in time. It's like a little tiny snapshot. But then they go back to not being held together anymore. Okay, so London dispersion forces are very weak forces, and it's referred to as an induced dipole because it's talking about nonpolar molecules. Okay, the next one is, So another thing about London dispersion forces is that it can take a nonpolar molecule like oxygen and help it dissolve into a polar molecule like water. Okay, because of that instantaneous dipole, there will be a weak attraction between the O2 and the polar molecule of water. Okay, so you would think oxygen would never dissolve in water, but it really does. And I mean, fish and sea life are alive because of it. And it's this London dispersion forces that makes that possible. Now, the next one on our list is dipole-dipole. This one is pretty obvious. You have two polar molecules that have a slightly positive end and a slightly negative end. We talked about that earlier in this video. So a polar molecule is going to be attracted to another polar molecule because we know that opposites attract. Okay, so the negative end of the one molecule is attracted to the positive end of the other molecule, and that is a stronger intermolecular force of attraction. Okay, so if you have again, we can have a dipole-dipole. Dipole-dipole, here we have an ICl. These two molecules look exactly the same. They are linear. They're both halogen atoms bonded to another halogen atom, but Br2 is completely nonpolar, whereas ICl is a slightly polar molecule because of the difference in electronegativity. So therefore, the boiling point of the ICl is going to be much higher than the Br2 because it has stronger intermolecular forces, because it has the dipole-dipole interaction. Okay, so you can see that the stronger intermolecular force of dipole-dipole gives it a higher boiling point. Okay, well, here's a little, just a little graphic of that same point. Then the last one in our category are hydrogen bonds. Now, hydrogen bonds are a special kind of dipole-dipole force. So a hydrogen bond is still considered an intermolecular force. It is not a full covalent bond. However, it takes place between only certain types of bonds. It has to have an NH bond, an OH bond, or an FH bond to form a hydrogen bond. Okay, so water has hydrogen bonding because it's made up of OH bonds. Okay, so the OH bonds are highly polar, so therefore it's a stronger dipole-dipole, and it's so special that we call it hydrogen bonds. Okay, here's another look at that. So the hydrogen bond, when you write it, is represented with a dashed line between the negative end of one molecule and the positive end of another molecule. And these are the strongest intermolecular forces. Okay, so the little acronym HOGS, that's how you can remember it. It's hydrogen and hydrogen bonds and only with HN, HO, or HF bonds. Where does the HOG come in? Okay. The electron hogs because it's a hydrogen bond. I don't know. It's cute. Okay, so the efficiency of the hydrogen bonding in water gives it the special properties. Okay. Another thing about the hydrogen bonding is it increases with the stronger electronegativity. So an HF hydrogen bond has a stronger attraction than an HO hydrogen bond or an HN. Okay, because remember, fluorine is our most electronegative atom. Okay, so just to conclude here, all of the forces are referred to as London van der Waals forces, any kind of intermolecular force. London dispersion forces are the weakest forces for only the nonpolar molecules. Dipole-dipole forces are next in strength, and those happen with molecules that have a dipole moment. And then the hydrogen bonding is the strongest of the three, and those are the special category of HN, HO, or HF bonds. Okay.